In this tutorial, I want to just give a quick overview of the new Tripper liftoff worksheet that we've added. So I'm going to go ahead and just open up the Sidewinder, the Tripper conveyor example file here. Um, Essentially, this is essentially just a profile that's been put in, and we can see here we've got a Tripper location here. Now, typically with trippers, we in the curves here we had this loading for extra liftoff case, which essentially was saying what radius would we need if the belt was 15% loaded to prevent liftoff. We can see if we look at the vertical curves here for that concave curve, we'd actually need a 376-meter radius to prevent the belt from lifting off just under the running belt tensions. Now this is again running belt tensions with that local section empty. So your conveyor's been loading in it, maybe stop loading, and you got that empty section that goes through, or when it's loading right up, if the tripper's at the head end and it's loading up to that tripper, you're essentially at full running or full loaded belt tensions, but that section is empty. So Sidewinder is saying we need 376 meters. Well, obviously on lots of trippers, we don't have that kind of room. So in the detailed page here, we can look at any of the cases we want. Let's just keep it simple. So we'll look at the full normal case. That's saying, okay, in that curve section, in this curve section, the tension is 156 kilonewtons when the belt's loaded. If the belt was 15% loaded, I'd need a 124-meter radius. So a lot of people say, all right, that's what we want to use for a minimum kind of tripper radius is 124. Other people use 25% loading. So if I went over here and I change this to 25 and I run it, it's going to be obviously a smaller radius. It's going to be something like 87 meter radius, because obviously we've got more material that's now loading. Basically the tensions are exactly the same. It's just changing that load percentage for that. We'd still need 348 if this section was empty. So that's historically how we've done this. The tension is actually calculated at all points in that curve. You can set the starting point, the ending point, the midpoint. By default, Sidewinder just uses all the points. If we go ahead and look at that curve, we can see these are our curved elements. And again, this is always the start of the element. So if we look at this, the fully loaded case, that ending, this is the last curve, and it would actually end, or the start of the next point would be 156 kilonewtons. And of course, if we look at our fully loaded case, it's 156 kilonewtons. So now if we go into this advanced tripper worksheet, if we will, it's essentially went ahead and found by default that tripper element, number 13. And again, that's 13 because in our conveyor profile, that's element 13. It's not on the vertical profile. Remember, the vertical profile just has all the IP points and things aren't cut up, and your easy profile has just got whatever 4 or 5 elements on it. It's actually the calculation point. That's point number 13 here. So it's automatically found that. We can put in, if it didn't find the right one, or if you had multiple trippers, you go ahead and enter that number and it'll update everything for us. Found the element height for that. It picked a length of 50 meters. Now this is irrelevant. This is just for plotting point purposes. If I change that to 60 or 70 or whatever I want, 80, it just plots that out. But that's purely just for plotting purposes. I grabbed the nominal belt mass. Again, if you want to work with a reduced belt mass or a high belt mass, you can go ahead and enter anything you want. Again, it's assumed that we don't have any loading of the material. The material loading kilograms per meter on this example file is about 555 kilograms per meter, so we can change that in a second here. And then it's given basically a wheel position. So this would be the contact point of that wheel. I kind of thought about putting the wheel center and a diameter, but then might be almost more confusing. So this is just the contact point, and that's reference to the center of the head pulley. So if I make this 20 meters, for example, it's going to move it over here, and I can move it up to whatever, 2 meters or a meter and a half or whatever, which is again above this ground line of where that element enters into the tripper station. So that's how that's referenced. We'll go back and say 25 and yeah, maybe a meter. So what's shown here is essentially four conditions: the empty, the fully loaded normal, the maximum running tension, and the maximum dynamic tensions. Now we can see if we just look at the full normal that we were looking at before, we can say, oh, that's 162, but wait a minute, we had 156. Why is it 162? Well, it's 162 because if we look at this pulley, if we looked at the curve section, which is what the curve calculations obviously get the tensions from the curve and the next element, this actually went all the way up to the head pulley and grabbed the pulley, the tension from the head pulley. So it kind of took the max of any of these, and which kind of makes more sense because of the fact that if the belt is lifting off, even though we've got a straight section going into that pulley, it's still part of the curve because the curve has really, created this much larger radius here. So it's automatically found that highest tension, if you will, for the liftoff. Um, I'm just entering 0 just to make the graphics a little bit cleaner for you guys to see. But we can see we've got actually the black line is our elements, each of those individual elements, and it's cut up into the number of elements that Sidewinder cut it up into, and then our head pulley. Um, this dotted line here that you see, this is the edge, the edge of the belt in the wing roll. Obviously, this would be in the transition going back to flat. So it's kind of nice just being able to see, in this case, we've got a 5-roll set. The black line would be the center or the bottom, our belt contact point right here. That dotted line was just the edge of the belt. That's all that was. But it's kind of nice to be able to see that, so you can see where hold down rolls at. Obviously it's not going to be right in the center because it would be running over material, so usually that's going to be up a little bit higher, maybe 1.1 or 1.2 meters, somewhere up in there. And then it just essentially shows what the catenary sag is for each of these different tensions. And again, you don't have to use these. You can use whatever, enter whatever your tension you want. You can see here for the 162, we're getting about, what was it, 0.6, 0.7 millimeters of displacement, something like that. Again, we've got our cut up elements here, so that's that. And if we actually had our wheel, our contact point was right there, it wouldn't even be touching the belt. If we moved it down and forced it down, we can see we got about 4 kilonewton meters. So this is just kind of a nice, like I say, it gives you what the catenary is going to actually look like, as well as what those forces are. And if I go ahead and just re-click this element, it'll just re-update all of my tensions. And so if we maybe look at the maximum dynamic tension, you can see the running is not that much different than the fully loaded. But our max dynamic is probably a starting, or maybe it's a braking case or whatnot. We can see with that tension, and if we move this up to, right, if our hold down roll was right at kind of the edge of the edge of the belt, or maybe a little bit above it, we can see we got about 6 kilonewtons of reaction force there. It's also kind of nice because we can come in here and look at, all right, if we do have a little bit of material loading, where's the belt actually located in that case? So we can say, okay, this was, I think it's about 550. Yeah, our material mass is about 550 in this example, which is 8,000 tons per hour, running at whatever belt speed we were, 4 meters per second. So 10% of that would be, if we put in a load of 55 kilograms per meter, we can see that drops that way down. But we'd still have, wouldn't even need a hold down roll with 10% belt mass, but this is a pretty high belt mass. Again, the calculations are always going to be from the tip of the pulley to wherever catenary sag's going to land. So obviously in this case the idlers would really be supporting the belt for all of these other cases and all these other tensions, but it's still nice. I like showing those to see that that's where it's really located. So anyway, it's just kind of a work page that I think people might find useful if you're working on tripper belts and want to get just kind of a little bit better feel of about what's going on and how much liftoff. I should mention that this liftoff distance, so if we looked at, say, again, let's just look at the fully loaded case. We've got the liftoff length is 53 meters, so that's 53 meters from here all the way down to where it completely hits the belt. So actually, we'd have to go to say 60 meters to be actually able to see it. So it's actually from 0 all the way to 53 meters is where it comes down to 0. Now the reality is I also added this 10 millimeters, so this is essentially where this distance comes down within 10 millimeters of the belt. So it's a little less conservative, but the reality is it's probably a little bit more realistic because don't have a perfect flat shaped belt. We've got this trough shaped belt and whatnot, so you're actually going to start coming into contact with the idlers, obviously somewhere in here or whatnot, because you've got your trough shape idlers in here that your flat belt's going to be contacting into. So that's all. The only difference between this is where it actually comes down actually to y equals 0. This is where it comes down to y, and I just randomly picked 10 millimeters as saying, okay, that's basically 0. You can see there's a 3 meter difference, but that gives you a nice feel for where that's going to, um, come back to contact under that specific tension. And I could easily put in any tension I want there. So if that was 250, I can go ahead and put in 250 kilonewtons of tension, and I can see my wheel reaction force if it was placed right there would be about 9 kilonewtons, and we'd have without the wheel, we'd have about a 60 millimeter liftoff distance. I guess I don't put in a curve with the reaction wheel because that's going to obviously pull that belt down into that curve. So as usual, always open for feedback and comments, and hopefully you guys find this useful. Thanks. Have a good day.